Hello everyone. This is lecture 5 of course PE 500. In the previous lecture, we have covered the second order differential equation, and we mentioned that there are two types, homogeneous and non-homogeneous. Homogeneous equation means that g of t equals 0, and non-homogeneous functions where g of t refers to a function or a constant. We have mentioned how to handle homogeneous equations and interpret the oscillation types such as undamped, overdamped, or critically damped. In this lecture, we are going to cover how to deal with non-homogeneous linear differential equations so that by the end, we will be able to deal with any linear differential equation, whether they are homogeneous or non-homogeneous. So to solve non-homogeneous linear differential equation that on this form, a second derivative multiplied by a plus the first derivative multiplied by b plus x multiplied by c, and there is a function f of t at the end, we need to find the general solution. And the general solution consists of two parts. The first part is called homogeneous solution, xh of t, and particular solution, xp of t. And in the homogeneous solution, we are going to solve the linear differential equation without the forcing function as f of t equals 0. And after that, we will find the particular solution to study the effect of the external force f of t. By finding both of them, we can combine both of them together to find the general solution that equals to xh of t plus xp of t. Again, the particular solution captures how the system behaves due to the external force or input f of t, and the homogeneous solution alone tells you how the system behaves if there is no external force f of t, and by combining both of them together to find the general solution, we are studying both sides with external force and without external force. The external input or force in engineering systems can be drug infusion over time, electrical stimulation of muscles, periodic heartbeats under stress, external loads during gait. So to model a real-world problem, we need to study the effect of these inputs to the system. To do that, there are two common methods. The first is called Method of Undetermined Coefficients, and the second is called Variation of Parameters. The method of undetermined coefficients is recommended and best used when you find that f of t is polynomial, exponential, sine or cosine, or a combination of them. And during solving the linear differential equation using this method, we are guessing a functional form for xp of t based on the function f of t. And based on that guess, we are substituting in the given differential equation to get the unknown coefficients. And for the second method, variation of parameters, we can use it as a general method than undetermined coefficients, and you can use it when f of t is not one of the standard forms. And during solving the differential equation using this method, we are involving the integration of the homogeneous solutions against f of t. So simply, you check f of t. If it's on these forms, then you can use the method of undetermined coefficients. Otherwise, you can use the variation of parameters. And we are going to understand the different steps for each of them after a while. So let's begin. Let's start by the method of undetermined coefficients. This method, as mentioned, involves guessing a form of a particular solution based on the given f of t. Then you can use that guess and substitute in the differential equation to find the unknown coefficient. Again, you can use this method when you find that f of t is one of the standard forms, polynomial, such as t raised to the power of n, exponential, such as exponential of a multiplied by t, trigonometric functions such as sine and cosine, or combination of them. Now, we can summarize the steps for the method of undetermined coefficients. First, find the homogeneous equation and solve it. Then, for step 2, for the particular solution, guess a form for xp of t based on the given function and solve it. Step 3, combine both of them together to find the general solution. In step 1, as noted, solve the homogeneous equation, simply set f of t equals 0, and by finding this, we can simply find the independent solutions based on the characteristic equation and the discriminant, as we illustrated in the previous lecture. If it's case 1, case 2, or case 3, you can guess the corresponding solution for that homogeneous equation. After that, in step 2, to guess the form, simply get the type of the equation and find the corresponding guess for that particular solution. Then you have now two solutions by the end. If you encounter that both solutions are similar, for example, cosine t here and cosine t here, simply multiply the particular solution by t or t squared to make it unique. So simply, we don't need to make any overlaps between the homogeneous solution or the particular solution. Once you encounter that, multiply the particular by t or t squared or t triple and so on until you make both sides are unique. As noted, we have t and we need to find the corresponding guessed for. And you can use this table to find the corresponding guesses for the different f of t functions. If it's exponential, simply the corresponding form will be like that. If it's sine or cosine, simply this will be the corresponding form. If it's t raised to the power of n, it's this form. If it's combination between t raised to the power of n and the exponential, then you can combine this and that together on this form. If it's a combination between the exponential and cosine, then this will be the corresponding form. So check f of t and find the guessed form. Use this guessed form, substitute in the differential equation, and find the constant or the coefficients. To understand these steps, let's solve an example. We have this equation, a linear differential equation, and f of t in this case is on the sine cosine form. So the corresponding guess when we solve the particular solution should be on this form. To follow the steps, let's start step 1, solve the homogeneous equation. And this can be done by setting f of t to be 0. What to do? As we mentioned in the previous lecture, simply check that they are here constants a, b, and c, and homogeneous. Then you can use the characteristic equation to set the second derivative to r squared, first derivative to r, and set the different coefficients or constants. Then you will retrieve this characteristic equation. After that, find the discriminant so that you can determine which case and the corresponding solution. So the discriminant is b squared minus 4ac. b squared is 16 minus 4ac minus 4 multiplied by 5 multiplied by 1 equals to 20. 16 minus 20 is negative 4, which is below 0 or less than 0. So we are in case 3, which is complex roots. After that, find the roots. Simply use the quadratic form, negative b plus minus the square root of the discriminant over 2a. You will retrieve that r1 equals to negative 2 plus 1i. And for the second root, will be similar to the first root, but instead of plus, it will be minus. Now, we got alpha and beta. Alpha is negative 2, beta is 1. Negative 2 and 1. Using alpha and beta, substitute in the corresponding solution, which is on this form, exponential multiplied by cosine and sine. Substitute, alpha is negative 2 to be like that. Beta is 1 here and here to be like that. Now we got xh of t, which is the homogeneous solution. Keep it until we get the particular solution. We have 3 multiplied by sine 2t. We mentioned that the particular solution will be on this form. If you return back here, we have omega. And omega in this case will be the coefficient or the constant multiplied by t. In f of t, omega here will be 2. So the particular solution will be a cosine 2t plus b sine 2t. Now we need to find a and b. How to do that? Simply, as noted, substitute in the differential equation. By substituting in the differential equation, you can retrieve the values for the constants or coefficients. We need the first derivative and the second derivative. So simply before substituting, find the derivative of the solution, the first and the second. So the first derivative of xp of t will be negative a sine 2t multiplied by 2, which is here, because the derivative of cosine is negative sine. And for the second part, sine will be cosine 2t multiplied by p multiplied by 2. For a second derivative, simply it will be cosine 2t multiplied by negative 2a multiplied by 2, which is negative 4a. And for here to find the second derivative, the derivative of cosine is negative sine 2t multiplied by 2p multiplied by 2, which is negative 4p sine 2t. Now we have the particular solution and the first and the second derivatives and the original differential equation. Substitute using these equations into the original equation. Simply substitute using the second derivative to here and substitute using the first derivative after multiplying by 4 here and using the original particular solution after multiplying by 5 here. And don't forget the right hand side. You will get something like that. Start to organize the parts here and group the terms together. You will retrieve something like that. Then find the coefficients of sine and cosine so that you can find the values for a and b from the left and right sides. So the coefficient of cosine will be negative 4a plus 8b plus 5a equals 0, because the second or the right hand side doesn't contain any coefficient for cosine, and the coefficient for sine will be negative 4b negative 8a plus 5b equals 3, as the right hand side has sine with a coefficient of 3. Now use these two equations to find the values for a and b. Simplify, you will retrieve that a plus 8b equals 0 and b minus 8a equals 3. Solve both of them together. You will get that b equals to 3 over 65 and a equals to negative 24 over 65. Using the values for a and b, substitute in the particular solution and write it to get it like that. Now we have the homogeneous solution and the particular solution. We can now get the final general solution by simply combining both of them together. Combine that and that, or sum both of them together, you will get the final solution to be like that. You may mention how to find the values for C1 and C2. Simply, if you have initial conditions, then you can substitute in this function to find the values for C1 and C2. Assume you are given that x of 0 equals 1 and x bar, or the first derivative of 0, equals 0. You can substitute. You will get two equations. By solving both of them together, you will find the values for C1 and C2. And we noted from a while that when you find overlapping between the homogeneous solution and the particular solution, then multiply the particular solution by t or t squared and so on until you make both of them are unique. So before saying that you completed the question or solving to find the final general solution, make a double check. Check that the homogeneous solution and the particular solution are unique. Simply, we have cosine plus sine, but here we have cosine multiplied by the exponential and sine multiplied by the exponential. So both of them are unique. If you encounter that this part is not here, and you found that here it's 2t and here it's 2t, for example, then cosine here and cosine here are similar, and sine here and sine here are similar. So simply multiply the particular solution by t. So you are multiplying here by t raised to the power of n until you make both of them unique. But in our example here, or our case, both of them are unique, so this will be our final general solution. Let's switch to variation of parameters. As noted, we are using it when the right-hand side is not on the standard forms, such as tan, such as ln, or 1 over t. And you can use a variation of parameters method as a general method. So you can also solve the previous question using the variation of parameters. And this method is recommended when you have a complicated f of t function. So how to solve it? We have 3 steps. Find the homogeneous equation and find the corresponding solution to get the homogeneous solution, as we did with the previous method, the undetermined coefficients, and then using the values of x1 of t and x2 of t, which are retrieved by the homogeneous solution as they are written on this form, move to the second step by letting the constants vary. How? Simply multiply the first solution by u1 of t and multiply the second solution by u2 of t. Now we need the values for u1 and u2 so that we can get the final particular solution. We can retrieve u1 of t and u of t using these two formulas, which can be integrated later to get them. So what are these two formulas? These are two standard formulas. The first derivative of u1 of t equals to negative x2 multiplied by f of t divided by w, and w here is the Wronskian value, and the first derivative of u2 of t equals to x1 multiplied by f of t divided by w. Again, w here is the Wronskian value, and this value simply can be retrieved by the determinant of this matrix. So how to fill this matrix? Simply set the first solution, a second solution in the first row, and their derivatives in the second row, like here and here. After that, find that the determinant, it's x1 multiplied by x2 bar minus x2 multiplied by x1 bar, which is here. We have now the value of w, put it in the denominator, and simply to avoid any conflict, if you are solving for the first solution, then here put the second solution. And if you are solving for the second solution, put here the first solution. And multiply both of them here and here by the right hand side, which is f of t. After substituting here and here, integrate both of them to find u1 and u2. To understand these steps, simply let's solve an example. We have the second derivative plus x equals to sec of t, and sec of t equals to 1 over cosine of t. Just keep this in mind as we are going to get the benefit of this later. As we noted, first step, solve for the homogeneous equation by setting f of t equals 0 and solve this. Check that the coefficients are constants and you are solving homogeneous equation. Then you can use the characteristic equation by setting this differential equation on this form. R squared plus 1 equals 0. Then get the discriminant b squared, which is 0, minus 4ac, which is minus 4 multiplied by 1 equals 4. So 4 minus 0 is negative 4 is lower than 0. Then we are in case 3, which is complex roots. Find the roots. They will be I and the negative I. So alpha will be 0, beta will be 1. In this case, alpha here will be 0. So the exponential of 0 will be 1. Beta is 1, beta is 1. So the final homogeneous solution will be like that. So now we have x1 equals cosine and x2 equals sine. Use these solutions, x1 and x2, and also sec of t, which is f of t, to move to the second and third step. Simply compute first the Wronskian matrix and the determinant of it, as we mentioned. Set in the first row the solutions and the second row their derivatives. So set here cosine, sine, and their derivative will be cosine will be negative sine and sine will be cosine. Find the determinant. Cosine square minus sine square equals 1, as cosine square plus sine square in the trigonometric formulas will be 1. Now we have what we need. Then substitute to find u1 and u2. u1 will be the integration of negative x2 multiplied by f over w. x2 is here, f of t is here, w is 1, so it will equal to negative the integration of sine multiplied by sec of t over 1. As mentioned, sec of t is 1 over cosine, so sine over cosine will equal 10. So the integration of negative 10 of t will equal to negative ln sec of t, as the integration of 10 is ln sec of t. We have here negative and ln, so we can apply the negative inside the ln to be power of negative 1. So sec of t raised to the power of negative 1 is 1 over cosine, which will be cosine. So the final answer would be ln cosine of t. For u2 substitute, we have x1, which is cosine, multiplied by f of t, which is sec over 1, cosine over cosine, or cosine multiplied by sec, which 1 over cosine will equal 1. The integration of 1 will be t. Now we have u1, u2, substitute to get the particular solution in this equation. u1, which is ln cosine of t, multiplied by cosine of t, plus t multiplied by sine of t. We got the particular solution, and we got also the homogeneous solution. Combine both of them together to find the final general solution. But as noted, if you got overlapping, multiplied by t raised to the power of n to make it unique. We have here cosine multiplied by a coefficient or constant, but here we have cosine multiplied by ln cosine, and both of them are different. We have here sine, but here it's sine multiplied by t, and both of them are unique. So all of the factors are unique. So the final solution is the combination or summation of both of them. So the final solution will be like that. So now we can solve the non-homogeneous linear differential equation using two approaches: the method of undetermined coefficients and variation of parameters, and we knew the different steps for each of them, and we solved an example in each method. Now we need to make a case study. In this case study, we are modeling a knee joint motion using second order linear differential equation, and human joints, like the knee, behave similarly to the spring mass damper systems, where the bones act as rigid bodies, and the ligaments and tendons provide elastic restoring forces like the springs, and the muscles and the synovial fluid provide damping effects. So we can simply model that using our system, which is a second derivative multiplied by m, the first derivative multiplied by c, and k multiplied by x, and we have a force here, f of t, which will be the external force or the external input. X of t is the displacement of the joint form equilibrium, and m is effective mass involved in motion, such as the leg segment mass, and c is the damping coefficient due to muscle resistance, k is the stiffness of ligaments or tendons, and f of t is the external force, which like the impact during walking or running. And similar to what we did in the previous lecture, we can analyze a different type of oscillatory behavior, such as undamped, underdamped, and forced oscillation. But here we will define a problem and we will solve that using one of the two methods illustrated in this lecture. And the problem says that the patient is undergoing rehabilitation after knee surgery, and we need to understand their recovery progress. And we are asked to model the motion of the knee joint when subjected to an external periodic force representing the gait dynamics. And we are given these parameters and initial conditions, where m equals 1, the damping coefficient c equals 0.5, and k is 4, and we have an external force equals to 2 cosine 3t. And the initial conditions, x of t equals 0.1, and the first derivative of t is 0. So we'll use our model, which is represented here, and substitute using the given parameters to get the following equation. If you notice, we have a linear differential equation, and it's non-homogeneous. And based on that, we can use the method of undetermined coefficients or variation of parameters to solve it. Which method to use? Simply, this is on the form of cosine, so we can use the method of undetermined coefficients. And if you are asked to identify the equation type and different configurations of it, simply it's non-homogeneous because we have force. It's second order because the highest derivative is the second derivative, and it's linear because the coefficients doesn't depend on t, and we have constant coefficient, so we can use the discriminant and the characteristic equation when you are going to solve the homogeneous part. And the final solution should be on the form xh of t and xp of t. So let's start by solving the homogeneous part. Simply substitute here by 0 for the force. And as we mentioned, we can use the characteristic equation because the coefficients are constants. So the corresponding characteristic equation will be r squared plus 0.5r plus 4 equals 0. We can get the discriminant, which will be b squared, which is 1/4, minus 4ac, which is 16, and it will be lower than 0. which refers to K3 complex roots. Find the different roots using the quadratic equation for R1 and R2. Then you retrieve that alpha is negative 0.25 and beta is 1.984. Substitute in your homogeneous solution, which is the guessed form, alpha here, beta here, and here. You will retrieve that the homogeneous solution should look like that. After that, use the method of undetermined coefficient to find the guessed form for the particular solution. We have a trigonometric function, sine or cosine, so the corresponding solution will be like that: a cosine plus b sine. Write your particular solution, and as noted, omega here will be 3, so the particular solution will be a cosine 3t plus b sine 3t. As we mentioned, we need to substitute in the differential equation. So let's compute the derivative, the first and the second. A cosine 3t, its derivative will be negative sine multiplied by 3 multiplied by a, and sine will be cosine multiplied by 3b, and the second derivative will be sine will be cosine negative 3a multiplied by 3, which will be negative 9a. Cosine will be negative sine 3b multiplied by 3 will be 9b. Plug xp and the other derivatives in the differential equation, we will get the following substitution. Start to group and organize the terms so that you can find the coefficient of cosine and sine easily. So the coefficient of cosine 3t will be negative 9a plus 1.5b plus 4a equals 2, because the right hand side has a coefficient of 2 and it's cosine. And for sine, it will be negative 9b, negative 1.5a plus 4b equals 0, because there are no parts for the sine in the right hand side. Now we have two equations. Simplify them so that you can get two simplified equations. Solve both of them together to find the value of a and b. The value of a will be negative 0.367 and the value of b will be 0.11. Using the values of a and b, substitute in the particular solution to get the final particular solution that looks like that. We have the homogeneous solution, the particular solution, substitute to get the final general solution that looks like that. This part is homogeneous and this part is the particular. Don't forget to double check that both solutions are unique. We have exponential multiplied by cosine and we have cosine. Exponential multiplied by sine and we have here sine. So all factors are unique. But we got two constants, C1 and C2. And now we need to find their values. Simply use the initial conditions, which are given at the beginning of the question. X of 0 is 0.1 and x bar of 0 is 0. Substitute by setting t of 0 in this equation. You will get e raised the exponential of 0 will be 1, cosine 0 will be 1, sine 0 will be 0, cosine 0 will be 1, sine 0 will be 0, and all of that will equal to 0.1. Simplify, you will get that C1 minus 0.367 equals 0.1, and by simplifying and solving for C1, you will get that C1 equals to 0.467. Now, we need to get C2. Simply apply the derivative to get x bar of t by applying the derivative to the whole equation of the general solution. Then substitute using t equals 0, and the right hand side will be 0, and substitute by the retrieved C1 value. Simplify the calculated equation. You will get by the end that C2 will equal to negative 0.107. Now we have C1 and C2. Substitute in the equation to get the final analytical solution that looks like that. Now we have an analytical solution, and we learned how to calculate the numerical solution using Python and MATLAB. We need to verify that both of them match together. So simply, we can update our model and plot both of them above each other to check if there are any conflict or both of them are matched. So go to scripts, lecture 05, lab exercise 1E in Python and MATLAB. In Python, we imported the necessary libraries, NumPy for mathematical operations, matplotlib for plotting, and we imported the function solve initial value problem for numerical solutions. We wrote the model. As we mentioned, we need to set it to first order differential equation as we did in the previous lecture. So dx by dt equals v, and dv by dt equals negative cv, negative kx plus the external force. And we here got the different arguments. So you can use this model or this equation or this function for the numerical solution. We define the values which are given in the question. We set the initial conditions. We set also the time span for 50 seconds with 2500 points. Then we wrote the analytical solutions that we solved from a bit, which would be the homogeneous solution plus the particular one, and also use the solve IVP and passed the function to find the numerical solution. Now we got analytical and numerical solution. We can plot both of them together using Matplotlib. We created a figure, plotted first the analytical solution in black, and plotted the numerical solution in red with dashed line style. We set the labels, the grid legend and title, and by the end we saved the figure and plotted it. When you execute the code, you will find a block that looks like that. At the beginning of around 10 seconds, there is a disturbance or there is oscillations with different amplitudes, but after that it settles with an amplitude of 0.4 and a negative 0.4. If you look closer to the two curves or two plots, you will find that both of them match together, the analytical and the numerical solutions, the analytical in black and the numerical in red, so that you can validate and to confirm that your final solution is correct. And if you switch the gears to MATLAB, we here set the initial parameters or the values for the parameters, the initial conditions, the time span for the simulation, also for 50 seconds and 2500 points. We created a variable to hold the analytical solution as we did in Python by combining the homogeneous solution and the particular solution. Then we used the ODE 45 and passing the new model to get the numerical solution. Now we have analytical and numerical solutions. We can plot both of them together, the analytical in black and also the numerical in red. We set the labels and titles, and don't forget to hold on and hold off the figure. Then we saved the figure, and as we mentioned in the previous lecture, in MATLAB, if you are executing a simple script and you need to write a function, you can add it at the end of the code. So we have here our model, xv, and we have the xdt and dv by dt, and we are returning both of them together, and these are the given parameters. If you executed the code, you will get the corresponding figure, and also, similar to Python, in the first 10 seconds, there are oscillation with different amplitudes, but it settles after 10 seconds between negative 0.4 and 0.4. So based on that plot and your problem statement or your given problem, you can confirm that periodic oscillation is suitable or can be accepted or not. So in this lecture, we have covered how to solve the non-homogeneous linear differential equation using two approaches, the method of undetermined coefficients and the variation of parameters. In the first method, you need to double check for given functions or set of functions. If you found them, you can use the guessed forms and start solving the problem. And otherwise, such as if you encountered a different geometric function such as sec of t, or find another function such as 1 over t or len of t, you can use the variation of parameters method. Either you are using this or that, you need to find the final general solution, which equals to the summation between the homogeneous solution and the particular solution. Based on that analytical final solution, you can plot it alongside the numerical one to validate your output and results. And by the end, we encountered a case study about the modeling knee-joint motion and applied that using Python and MATLAB. And in each of them, we plotted the two solutions to validate our steps.